Scene script. Have you ever wondered what happens when two black holes collide? Well, let's dive into the vast expanse of cosmic wonder and explore the mysteries of black hole collisions. Picture this. Two monstrous cosmic entities, black holes, each with a gravitational pull so strong that not even light can escape, spiraling towards each other in a deadly dance. As they inch closer, their gravitational forces tug at each other, creating a spectacle of warped space and time. This is not a mere celestial tango, but a violent merging process. When black holes collide, they don't just combine into a larger, more massive black hole. Oh no, it's much more dramatic than that. They send out ripples, like those you see when you throw a stone into a pond. But these aren't ordinary ripples. They are gravitational waves that surge through space-time, the cosmic fabric that intertwines space and time as we know it, a concept popularized by none other than Albert Einstein in his theory of special relativity. Now, these gravitational waves aren't just a fancy term. They carry valuable information about the events that cause them, in this case, the collision of black holes. They're like cosmic messengers telling us stories of the universe's most violent and cataclysmic events. And guess what? We can detect these messages right here on Earth, thanks to gravitational wave detectors like the Laser Interferometer Gravitational-Wave Observatory, or LIGO, which made the first detection of gravitational waves from merging black holes in 2015. But there's so much more to this cosmic drama. As these waves of distorted spacetime spread out, they interact with each other, influencing their paths and intensities. This is where things get pretty complex, and our understanding of these phenomena continues to evolve. So, when black holes collide, they send shockwaves throughout the universe, altering the very fabric of spacetime. They are not just celestial behemoths, but cosmic maestros, orchestrating a symphony of gravitational waves that echo through the cosmos. Stay tuned as we unravel more about these fascinating celestial events in the upcoming scenes. Now imagine these space-time ripples spreading outwards. What do you think we call these? Just as a stone thrown into a pond creates ripples across the water's surface, the violent collision of black holes sends shockwaves surging through the very fabric of the cosmos. These cosmic ripples are what scientists refer to as gravitational waves. When black holes, these enigmatic entities with gravitational pulls so strong that not even light can escape, merge to form even more massive black holes, the process sets off a chain of events in the universe. The merging event is so catastrophic that it disrupts the equilibrium of spacetime, causing it to oscillate. These oscillations travel at the speed of light, producing gravitational waves that propagate through the cosmos like ripples on a pond. Now, these gravitational waves are incredibly elusive. They're so subtle that for a long time, their detection was considered nearly impossible. However, with the advent of ultra-sensitive detectors such as the Laser Interferometer Gravitational-Wave Observatory, or LIGO for short, we've been able to detect these elusive waves. Imagine LIGO as a cosmic microphone tuned to the frequency of the universe. It listens to the whispers of the cosmos, capturing the echoes of cataclysmic events like black hole collisions. In fact, it was LIGO that made the first ever detection of gravitational waves from merging black holes in 2015, a discovery that sent shockwaves through the scientific community. So, what are these gravitational waves exactly? Well, they're essentially distortions in the fabric of spacetime, caused by some of the most violent events in the universe. And these distortions carry with them information about the events that caused them, allowing us to study these far-off cosmic occurrences in unprecedented detail. So, gravitational waves are the echo of black hole collisions, and we have sophisticated devices to detect them. Our understanding of the universe has been vastly expanded by these cosmic ripples, and with every new detection, we're getting a clearer picture of the universe's most mysterious phenomena. Now, what if we could model these black hole collisions and gravitational waves in more detail? Let's dive into the fascinating world of supercomputers and advanced simulations. A new supercomputer model has been developed by the Simulating Extreme Spacetimes, or SXS, team. This model is designed to simulate black hole collisions and the resulting gravitational waves with a level of detail that's never been achieved before. What sets this model apart is how it takes into account the interactions between gravitational waves. Previously, these waves were treated as independent entities, riding through the universe without influencing each other. But the SXS team has gone a step further. They've incorporated what's known as nonlinear effects into their simulations. Nonlinear effects, as explained by Keith Mittman, a graduate student at the California Institute of Technology and a member of the SXS team, are similar to what happens when waves on a beach crest and crash. They interact and influence each other rather than ride along by themselves. Applying this concept to something as violent and chaotic as a black hole merger, the team expected to see these effects, but had not seen them in their models until now. Mittman further elaborates that the team's new methods for extracting the waveforms from their simulations have made it possible to see these non-linear effects of gravitational wave propagation. This innovative model is shedding light on the complex interactions that occur during a black hole merger and the propagation of gravitational waves. It's like having a high-definition telescope that can peer into the very heart of these cataclysmic events. By simulating these collisions and gravitational waves in greater detail, we're gaining a deeper understanding of the universe and the fundamental laws that govern it. From the violent dance of merging black holes to the subtle ripple of gravitational waves, this supercomputer model is helping us unravel the mysteries of the cosmos. This new supercomputer model helps us understand the intricate details of black hole collisions and the propagation of gravitational waves. Why does this matter? What can we learn from these simulations? These questions might be swirling in your mind. Let's delve into the implications of this supercomputer model. Our understanding of the universe and its workings is largely dependent on the ability to test and verify our theories. The new model developed by the Simulating Extreme Spacetimes (SSS) team provides an opportunity to test one of our most fundamental theories, Albert Einstein's theory of general relativity. This theory has stood the test of time for over a century, but it has its limitations, especially when it comes to explaining the mysteries of black holes. The SXS team's supercomputer model allows us to simulate black hole collisions in greater detail than ever before. By taking into account the nonlinear effects, the interactions between gravitational waves as they propagate outwards from the collision, this model could help put general relativity to the test in the realm of black holes. It's a revolutionary approach that could either solidify our understanding of general relativity or point us towards its limitations, paving the way for new theories and discoveries. Moreover, these simulations are not just about testing theories. They also have practical implications. The model can help scientists on Earth learn more about the events that launch gravitational waves, the ripples in space-time that we can detect using gravitational wave observatories like LIGO. By better understanding these events, we can improve our detection methods and potentially uncover new astronomical phenomena. The potential of this new supercomputer model is immense. It provides a clearer picture of black hole collisions, expands our understanding of gravitational waves, and pushes the boundaries of theoretical physics. It's a testament to the power of cutting-edge technology and the relentless human curiosity to understand the universe. So the mysteries of black hole collisions continue to unfold, and with every new discovery, we get a step closer to understanding the secrets of the universe.